Okay, let us start the second talk. It's a pleasure to introduce Henry Liu, who will tell us about invariance of elliptic genus under wall crossing.
Okay, great. Thanks for having me here. Yeah, so I want to explain today a small result in modern enumerative geometry. And my understanding is that most people here have backgrounds in integrable systems, so I will try to start with an explanation of this result in a very simple case, and then we'll try to move our way up into full generality. Okay, so that X for me will be a smooth, proper scheme over C. Everything in this talk is over C. If you want, you can imagine a smooth projective variety. I certainly do. And X will have the action of some algebraic torus of rank R, where if you want, R for now could be 0. Okay, but later it will be very important that it's not. This is the action of some algebraic torus. And associated to this data, you can think about some equivariant cohomology theories. And essentially there are 3. So you can think about the T equivariant cohomology of X. You can think about the T equivariant K theory of X. And you can think about this thing called the T equivariant elliptic cohomology of X. And these are modules for the T equivariant cohomology of a point, the T equivariant K theory of a point. And here there is going to be some T equivariant elliptic cohomology of a point. And to make somehow the comparison completely accurate, you should really be thinking about spec of these things. And I'm not going to talk so much about the elliptic stuff for today, because that's Andre's job next week. But here, equivariant elliptic cohomology is already a scheme. It's some proper scheme as opposed to some affine. Okay. So non-canonically, you think of this this underlying base as some number of copies of C, R number of copies of C, and more canonically, you can identify this with the Lie algebra of T. And similarly, the T equivariant K theory of a point, spec of it, is canonically identified with T, which will be some number of copies of C star. In fact, R number of copies. And over here, you're going to have R copies of an elliptic curve. Yes. Yes. Right. Okay. And the way to get from one to the other here is to take the exponential map. And the way to get from C star to this elliptic curve here is to modulo by Q the action of shifts under the co-character lattice of T. So here we're thinking about this elliptic curve E really as some kind of quotient of C star by shifts by Q. Okay. So here Q is the E to the, say, I pi tau, where tau is the elliptic modulus. And for this talk, Q will have norm much smaller than 1. Okay. Very concretely, I assume everyone is familiar with T equivariant cohomology. Here you think about equivariant differential forms, and you think about their pullbacks and push forwards, their integrals. Thinking about T equivariant K theory means you're working with T equivariant coherent sheaves, and you're thinking about their pullbacks and their push forwards. So in particular, in T equivariant cohomology, push forward to a point is just integral. And in T equivariant K theory, push forward to a point is Euler characteristic of sheaves. Okay. So the elements of these cohomology theories are going to be In the affine cases, fairly straightforward, but also in equivariant elliptic homology, these are sections of line bundles on these schemes. And in particular, I'll be writing down some quantity which you're supposed to think of as some quantity in equivariant elliptical homology of a point. So it will be some section of some line bundle on some number of copies of an elliptic curve. And in particular, there's one sort of very special section which I'll be concerned with, which is the odd Jacobi theta function. Okay, so for a coordinate x on C star, right, so we saw some theta functions this morning. They were all sort of written additively for some coordinate on C. So here we sort of just exponentiate everything. We're writing things as functions on C star. So this will be 1 minus x inverse product as n ranges over the positive integers, 1 minus q to the n x, 1 minus q to the n x inverse. And for now, we're going to treat this very sort of formally. This is some element in the ring valued in Laurent polynomials in X, formal power series in Q. Okay? And for convenience later, we're going to give a name to this part of this infinite product. This part is often known as a Q-Pockhammer symbol. We'll call this phi of X. Okay? And this theta of X is you can check that it's a section of some degree 1 line bundle on E. Put slightly differently, you can check that it satisfies the Q difference equation, that if you shift X by Q, you get some overall factor Qx inverse of the original function. If you unravel what it means to be some degree 1, some section of a degree 1 line bundle, this is exactly what it means. Okay. Okay, so now I can tell you what is elliptic genus. Okay. So first, we can take this kind of scalar function and extend it to a function of vector bundles. So we can extend to vector bundles E on our scheme X over there. And by the splitting principle, you're allowed to think of E as some sum of line bundles. Let's say Li. And we'll say that capital theta of E is going to be the product over each of these line bundles of theta function of Li. Okay. And similarly, we can extend this function phi. So we'll have some function capital phi, also a vector bundles of E. This will be some product of small phi of Li. And these will be, again, formal power series in Q, but now valued in something like the equivariant K group. So the coefficients of our series in Q will be something like coherent sheaves or vector bundles. Okay. And then we define the elliptic genus of X. This is the quantity E of X. And it will be a function of some formal parameter, Y. This is the sheaf Euler characteristic. So Euler characteristic here means alternating sum of sheaf cohomologies for X of theta of the tangent bundle of X. Okay, so here it's very important that X is smooth. And these Q-Pockhammers, these begin with constant term 1. So you're allowed to invert them in the ring of formal power series. So down here we're going to have phi of the tangent bundle, phi of the tangent bundle du. Okay. And to be very clear, this is some element which is a power series in Q, Laurent polynomials in Y, valued in the T equivariant K theory of a point. Say again? Yes. I forgot a y here. Thank you. Good. Okay. And sort of the simplest situation in which you can think about this is when the t action on x has isolated fixed points. Okay, so if t fixed locus is a whole bunch of points, isolated points, then by t equivariant localization, you can write this as a sum over these points of sort of the restriction of this integrand with some contribution from localization. And it will be, each term will be some product of weights, t weights, of the tangent space at each of the fixed points of theta function of y times the weight over theta function of the weight itself. So this is really some kind of function, meromorphic function on the torus T. Okay, and it's really something very, very concrete. This is really just some kind of meromorphic function on T. Oh, I see. Here. Yes, that's right. Right. So maybe I can say more precisely. This is some group of vector bundles or coherent sheaves with the usual sum map and formal differences. Yeah. Okay. Right. So I claimed earlier that this is supposed to be some elliptic quantity, but is it really elliptic? It should somehow satisfy some nice Q difference equations. And you can check that if you take this quantity and you shift, so let's say the coordinate, so let's say T has coordinates Ti, then you can check that under shifts of these coordinates, you're going to get some sum, and there will be some prefactor which comes out. And this prefactor looks like some monomial in y with some exponent, which will depend on the weights of the tangent space. And the same product here. And so you want somehow this factor which came out to be independent of which fixed point you're on, so that you really, this quantity really descends from this torus to some kind of meromorphic function on the elliptic curve E itself. Okay. And a simple way to somehow make this constant over all fixed points, simple case, is that this quantity in the exponent, sum over all the weights in the tangent space, paired with the co-character that you're shifting by, you want to impose that this is actually some multiple of n, and then you want to specialize y to some nth roots of unity. In this kind of setting, this prefactor is 1, and everything is good. And in fact, this condition which I've written here is basically equivalent to the condition that the canonical bundle of X admits an nth root. Okay. So later on, we're going to see a lot of specializations of this variable y to nth roots of unity, and we'll see some conditions on whether or not roots of the canonical bundle exist. And sort of all those conditions morally come from the requirement that something has to behave elliptically. Okay, so that's, yeah. small t, so small t is my notation for the coordinates on the torus t. Okay, so these weights W will secretly be some monomials in these t. And so you can maybe shift T1 by Q, say, and you can see what happens to these rational functions. Yeah. Okay. It's an equation. That's the definition. Okay, so now let me say something about wall crossing. So the wall crossing procedure which I want to think about is somehow a fairly general procedure. Right, so wall crossing. Let me say the setting first. So the setting is that you're going to start off with some M, so-called master space. And M will be a proper, same conditions as above, proper, smooth scheme with the action of T again, but also a commuting action of some new one-dimensional torus C star. And this master space will roughly look like this. It will be the C star fixed locus, so M C star fixed locus, will have three pieces, Z minus, Z plus, and Z naught. Okay, so this is part of what the master space should look like. And Z minus will be some kind of divisor. It will be the zero locus of some section psi minus. Where this is some C star weight -1 section of some line bundle. And similarly, we're going to have some divisor Z plus, which will be some section of some zero locus of some section psi plus. And then we're going to have some slightly more complicated locus, which may be lower dimensional, may have many components, may not be pure dimensional, and this will be Z naught. Okay. So in this kind of setting, we can obtain some kind of relationship between integrals on Z minus and integrals on Z plus in terms of some correction terms which come from Z naught. And this will be some kind of quote unquote wall crossing formula from Z minus to Z plus. Because in practice, these master spaces, the Z minus and Z plus in these master spaces will somehow be stable loci for some variation of the stability condition. So maybe you have some kind of locally constant behavior as you vary your stability condition, and on one end the stable locus is Z minus, and on the other end the stable locus is Z plus, something like that. So I want to quickly explain how to get this relation that I'm talking about. So we'll think about the Euler characteristic on M of some coherent sheaf F. This is some coherent sheaf. And by C star equivariant localization, I can write this as some Euler characteristic on Z minus of F restricted to Z minus with some correction from the Euler class of the normal bundle. And I'll have another term, Z plus, restriction of F to Z plus, Euler characteristic of the normal bundle of Z plus inside X. And then I'll have some more complicated term, which will correspond to Z naught, restriction of F to Z naught, Euler characteristic of the normal bundle of Z naught. inside X. Okay, so far nothing super interesting has happened. And these normal bundles n minus and n plus, these are really line bundles because we assume z minus and z plus are really divisors inside the master space. And now we want to sort of extract some relation between the term on z minus and the term on z plus. And the way that we do that is we apply some kind of residue in the following sense. So we notice that the left-hand side, m we assumed was proper. And somehow proper push forwards preserve coherence. So this is really some element inside the T cross C star equivariant K-theory of points. Right? It's really just some Laurent polynomial in whatever equivariant parameters you have. But each term on the right-hand side will be some non-trivial rational function of the coordinates on T and the coordinates on C star. Right? And in fact, you can be very precise about where the poles of these rational functions can be. Okay, so here you're going to get rational functions with poles at things like s to the k. So maybe I can say the coordinate on C star we'll call s, the coordinates on T we'll call T. So we'll get poles at s to the k, T to the mu is equal to 1 for some integers k and for some T weights mu. Whereas on the left-hand side, you really only have poles around 0 and around infinity. So what you do is you hit everything. You apply the map which sends f to some kind of contour integral f ds over s, maybe with a normalization to pi I, where this contour gamma sort of encloses every pole except the ones at 0 and at infinity. So in the middle, you're going to have a whole bunch of other poles. And we want the contour gamma to enclose all of these poles. What's the result after applying this map? The left-hand side has no poles enclosed by gamma, so it will become 0. The first two terms, these are just Euler classes of line bundles. So in K-theory, Euler classes look something like 1 minus maybe normal bundle dual, something like that. And this normal bundle here we said has weight minus 1 or weight plus 1. So it's really some rational function like 1 minus s plus minus times some line bundle. So there's some simple pole. But anyways, the point is that after applying this map, somehow the contribution from the normal bundle really goes away, and you really get some integral over z minus of the restriction of f to z minus. And then you're going to specialize something like s is equal to normal bundle minus something like that. And then similarly, you'll get the same kind of contribution for z plus, where s is specialized to something. And then you're going to get some complicated term. So let's call this map res. You're going to get some complicated term, which is the residue of this stuff over z naught. And the game somehow that we play in this field of wall crossing is we try to somehow control what this stuff is. We try to engineer situations where this extra stuff is as simple as possible, so that you end up with as simple as possible wall crossing formulas. And specifically, somehow, the case of how to do this for elliptic genus, I don't think has really been systematically studied yet. And so I want to explain how it's going to work. So for elliptic genus, you start off by integrating over m some quantity which looks like theta of y times the tangent bundle of m over phi tangent bundle of m phi tangent bundle of m du. Okay, so this is some formal series in Q valued in coherent sheaves or formal linear combinations of coherent sheaves. And if you execute this sort of algorithm, this wall-crossing algorithm, which I just explained, you'll get some relation which looks like 0 is equal to some numerical factor times the elliptic genus of Z minus the elliptic genus of Z plus. And then you'll get some contribution from this annoying Z naught. There will be some stuff which is independent of S. And then you'll get the contribution from the normal bundle, which looks something like theta of y times the normal bundle over theta of the normal bundle itself. And you want to know, when does the residue of this thing vanish? Okay. So the simplest possible wall-crossing formula is that nothing happens as you cross the wall, right? So we want this to vanish. And in fact, there's a very simple way to make it vanish. Maybe I'll state this as a theorem, even though it's not really some very complicated result. So if you write the normal bundle of Z naught inside the whole master space, so this is some normal bundle of some C star fixed component. So C star acts on it, and it will split into pieces depending on the C star weight. So we'll call those pieces n naught sub k. Okay, so k ranges over all non-zero integers. And the condition is that if the sum over these k of k times the rank of n0, the kth graded piece, if this is congruent to 0 mod capital N for some integer capital N, then the elliptic genus specialized to an nth root of unity of Z minus is going to be equal to the elliptic genus of Z plus specialized to the same nth root of unity. So zeta n is an nth root of unity, and for technical reasons, this should not be equal to 1. So it's really some non-trivial nth root of unity. Okay. And somehow this result is not really hard to prove, because all you have to show is that upon such a specialization to an nth root of unity, that this rational function sort of has 0 total residue. And I'll just briefly say the way to show it, because it's very easy. The idea is that after this kind of specialization to a root of unity, what is this residue? It's some kind of integral of some one form. And you can show that after the specialization, the one form is actually pulled back from an elliptic curve, which looks like C star. This is the C star which carries the S, modulo shifts in, right. And so, and the contour which we're integrating over, somehow this encloses all of the poles of this meromorphic one form on the elliptic curve. And so by Cauchy residue theorem, that sum will vanish. Okay, so my point is that it's not some super complicated result. Okay. So maybe at this point I can say that in the literature, there's many different constructions of master spaces depending on what you want to study. Historically, the sort of first one was due to Thaddeus, who was studying variation of GIT quotients. And you can plug Thaddeus's master space into this machine. It will satisfy all the conditions I've written down. And you can obtain some statements about what happens to elliptic genus under variation of GIT stability condition. And so there, so sort of every nice variation of GIT will be some kind of flip. And the condition which I've written down translates to something about the dimensions of the exceptional loci on either side of the flip. And so if such a condition is satisfied, then elliptic genus will be invariant under variation of GIT. Okay, so this is related to some previous results of Totaro. So I'm sure it was known to some experts in the field. But what I sort of, my personal interest in all this comes from a slightly more general setting where we think about how to remove this assumption that things are smooth. Yeah. Okay. Oh, okay. Yeah. Okay. So the hypothesis that we had throughout that the spaces we're working with are smooth, this is very restrictive, especially in modern enumerative geometry where the moduli spaces we consider are often not smooth. They're very, very far from smooth. In fact, you can think of things like Hilbert's scheme of points on C3, which not only is not smooth, it contains sort of every possible singularity known to mankind. And so in modern enumerative geometry, okay, well, sort of the local formal singularities, yeah. It satisfies Murphy's law. So in modern enumerative geometry, we do the following sort of replacements. Instead of thinking about schemes, we think about so-called derived schemes. And I find locally this just means that you replace all the rings that you used to think of by some kind of DG rings. And you replace all the modules you used to think of with some kind of DG modules. And the smoothness condition we replace with so-called quasi-smoothness condition. Now, I'm not really qualified to talk about derived algebraic geometry, but somehow the combination of having some derived scheme which is quasi-smooth, this is approximately equivalent to the more classical notion of having a regular scheme plus what's called a perfect obstruction theory. And in general, this regular scheme is going to be very singular. And what's a perfect obstruction theory? So we'll abbreviate this as a POT. A perfect obstruction theory is kind of locally like this. It's kind of like you want to study scheme X. You want to study your scheme X, but X is horribly singular. So you find some way to embed X into some smooth scheme M as the zero locus of some section of some vector bundle, E. E is a vector bundle. S is a section of it. And a perfect obstruction theory is kind of like some way to carry this kind of local presentation of your space around in a sufficiently functorial way. So this is some sufficiently functorial way to record this kind of local data. And in this kind of situation, especially when you have especially when this local picture is not just local, it's really global, you can replace things like the fundamental cycle of your space X, or the structure sheaf of your space X, were things that are much more well behaved. So you replace, there's some virtual version, virtual fundamental class, which if you call this inclusion I, then the inclusion of this virtual class looks like the virtual class on M capped with the Euler class of E. So, and similarly, you can think about replacing the structure sheaf with so-called virtual structure sheaf. And on the ambient, smooth ambient space M, this kind of looks like the structure sheaf of M capped with some K-theoretic Euler class of E. And the tangent, what used to be the tangent bundle of X, is replaced by so-called virtual tangent bundle, which in this case, sort of, if you think about how you can deform around on X, it's kind of like you can deform on M up to some obstructions which are specified by the bundle E, right? Because you want to preserve the fact that you're staying within the zero locus. So this is going to be something which looks like the tangent bundle on M minus E. This is some element inside the K group. Okay, so that's the brief outline of how to sort of upgrade yourself out of the case where you're smooth. So now we imagine the case where we have some scheme with perfect obstruction theory. And we want the perfect obstruction theory to be of a very particular form. So suppose X is a scheme with perfect obstruction theory such that the virtual tangent bundle has some very symmetric form. It looks like some coherent sheaf F minus the dual of the same coherent sheaf F, maybe up to some twist by some equivariant weight, which we'll call Y. Okay, so X here again is still carrying some action by some torus T, which now we really want to be non-trivial. And this Y is some T weight. So such perfect obstruction theories, we usually call them equivariantly symmetric. And somehow this is a hallmark of something which I want to mention later called Donaldson-Thomas theory. But anyways, in this kind of setting, we can define the so-called virtual chiral elliptic genus. This is some upgrade of the elliptic genus I wrote down earlier. So again, this will be some invariant, which is supposed to be some elliptic cohomology invariant of X. Except it's virtual, and somehow it's half of what we used to have before. And the formal variable Y in the previous case is now really carries some geometric meaning. It's some weight of the equivariant torus T. Okay. So this will be, so this is the definition. This will be again some Euler characteristic on X of the virtual structure sheaf twisted by half of the so-called virtual canonical. And on the bottom, we're going to have what we used to have. So phi of virtual tangent bundle, phi of dual of the virtual tangent bundle. Okay. Right. So here the virtual canonical just means that of the virtual tangent bundle dual. And I'm not going to worry so much about whether or not a square root really exists. That's some technical point. So this quantity, which I just wrote down, can be compared with what I wrote down earlier in the case where I have some equivariantly symmetric perfect obstruction theory. And the comparison comes from the observation that if I think about what does 1 over theta of the virtual tangent bundle look like, well, the virtual tangent bundle is something like F minus F dual up to some twist. And you extend these thetas and phi's to all of the K group multiplicatively. So this is really theta of F, and then up here I'll have theta of Y. Sorry, I think I need a Y inverse. Y inverse. Y inverse F. So this is almost what we had before. Before we had something in the denominator, and then y times the same thing in the numerator. Here we have some unwanted duals, and to get rid of these duals, that's why we need this twist by half of the virtual canonical. This is some point which is technical but important. So this is after twist by kx virtual 1/2 up to some factor in front. You're going to get theta of yf over theta of f. So then it should not be surprising that there's some virtual version of the theorem which I wrote down over there. So it used to be that we think about some topological criterion for the normal bundle and not. Now the role of the normal bundle and not is being played by this sheaf F. Okay, so the statement is that, right, the virtual version of the normal bundle, so again, in the same sort of master space situation, write this in the form F naught minus Y inverse F naught dual. This is possible because it's really just the C star moving part of the virtual tangent bundle up there. And then you have some topological criterion. Like if, so again, these are some sheaves on some C star fixed locus. They decompose into pieces graded by C star weight. So if the sum over K of K times the rank of the kth weight piece of F naught, if this is 0 modulo n, then you will have the invariance of virtual chiral elliptic genus. Then elliptic genus minus some nth root of unity, chiral virtual of Z minus is going to be equal to virtual chiral elliptic genus specialized at nth root of unity of Z plus. And the proof is going to be exactly the same. Okay, so in maybe my remaining 10 or 15 minutes, I don't know, I want to say something about the primary use case of this, which I care about. Somehow to so-called elliptic Donaldson-Thomas theorem. So maybe I'll start off by saying what is regular Donaldson-Thomas theorem. Okay, so we have a space Y. Y is a smooth, quasi-projective. For now, maybe for simplicity, we can just pretend it's really projective. 3 Calabi-Yau. And again, we assume that there is some, okay, I suppose if I want some torus action, I shouldn't, it really should be quasi-projective. Okay. Such that the Calabi-Yau 3 form, which is trivial, but maybe not equivariantly trivial, we assume that the Calabi-Yau 3 form has T weight Y. Okay. And you can consider a space called M alpha. And this is the moduli stack of coherent sheaves E on Y. Okay. Such that, so the entire moduli stack has infinitely many components indexed by the Chern character of E, which here we're going to set to be alpha. Okay, so alpha is some elements inside the ordinary cohomology ring of Y. And then for whatever notion of stability condition you have, you can think about the semi-stable locus, SST, with respect to some stability condition, which I'll call sigma. Okay, so sigma here is some stability condition. You're somehow free to pick whatever your favorite notion of stability condition is. What I'm about to explain will sort of be agnostic about which stability conditions you think about. So this is the locus of all sigma semi-stable E, and inside it there will be a locus of sigma stable E. And now, under the assumption that the semi-stable locus is equal to the stable locus, so we were explained to this morning about how stable objects have no automorphisms, and having no automorphisms means somehow the locus that you're thinking about is really not a stack. It's really just some scheme or some variety or something that does not exhibit stacky behavior. Okay, so in that kind of setting, we can think about things like elliptic genus. If semi-stable is equal to stable. Yeah, sorry, I'm sweeping some things under the rug. So there I wrote some moduli stack, and then these sort of stable and semi-stable loci live inside the are loci inside the rigidification of the moduli stack, where you get rid of the C star that you're thinking of. Right. Yeah, there's some technicalities here which I really don't want to focus on. But in the case where you have no sort of strictly semi-stable objects, then the sigma semi-stable locus has a perfect obstruction theory. Okay, so with virtual tangent bundle at the points, so this is a moduli space of sheaves. Its points are isomorphism classes of sheaves, and the virtual tangent bundle at this point E looks like X on Y of E with itself. This is the usual deformation theory of sheaves. Okay. So X here just means alternating sum of X Ks. And sort of many variations of this theory are possible, but for now, let's just think about this. I mean, you can think about the case where you think about moduli of coherent sheaves with some fixed determinants, or you think about maybe Y is not compact, but it has some compact piece sitting inside it, and you can think about compactly supported sheaves. What I'm about to explain is somehow agnostic to all of that. It doesn't really care. So in this kind of setting, you can define the so-called elliptic DT invariant, which I think these days is starting to be studied by both physicists and mathematicians. And this elliptic DT invariant is just dt elliptic over 2 minus y alpha sigma. So it will depend on which components of the it's attached to each component of the moduli space. It will depend on your stability condition, and this is really just the virtual chiral elliptic genus of the sigma semi-stable loci of class alpha. And you can start to ask, what is the wall crossing behavior for elliptic DT invariants as you vary your stability condition sigma? And this kind of wall crossing problem has been studied in ordinary cohomology and maybe in even in K-theory, but not so much with elliptic stuff. But in particular, there have been master spaces which are already constructed by people like Mochizuki or people like Joyce. Or in simple cases, you can really just use the original master space due to Sadius. So maybe let me give an example. Suppose that you're at a simple wall. The wall is simple. So simple here is some actual technical term. And it means that you're thinking about some one parameter family of stability conditions. And maybe over here you have some stability condition called sigma minus. And over here you have some stability condition called sigma plus. And the only point in this one parameter family where you have strictly semi-stable objects, where the inclusion here is really some strict inclusion, is some point in the middle, which I'll call sigma 0. And the condition that the wall is simple, so here you have semi-stable is not equal to stable. But everywhere else, you have semi-stable is equal to stable. And so the idea is that you can have sheaves E, which and as you vary the stability condition, it's not clear if that's a question or. Okay. But so you imagine varying your stability condition until you hit this point, sigma naught. And the condition that the wall is simple is that a priori your sheaf could split into many sort of, into a sum of many semi-stable pieces at this wall. And the criterion that the wall is simple means that you only really split into two pieces. Okay. Under this kind of assumption, you can construct a master space. So splits into two pieces, or maybe strictly speaking, less than or equal to two pieces, not more. In this kind of setting, you can construct a master space, and you can execute the procedure which I explained earlier. So you can apply the theorem which I wrote down earlier. Okay. So then a master space exists. And in particular, this complicated locus, which provides for you the wall crossing term, is the locus of points E inside M alpha semi-stable at sigma 0, such that E splits as E1 plus E2, and maybe E1 and E2 have the same slope under your stability condition. Okay. So this is the sort of complicated C star fixed locus in the master space. And so it's not so hard to see. I assume that's also not a question. So the virtual normal bundle here looks something like the cross terms when you try to compute x of E with itself. So here you're going to have something like x of E1, E2, plus x of E2, E1. And the way that the C star acts on everything is that the E1 here has C star weight 1. So if we call the coordinate of this C star S, then here we're going to have some S inverse, and here we're going to have an S. And by Serre duality, sorry, this should be a minus sign. And by Serre duality, this looks like x, this is isomorphic to x of E1, E2 dual with an extra factor of y inverse in front, plus something like this, right? So I've written the virtual normal bundle in the form that's required by the theorem. I've written it as where did it go? As some sheaf minus y inverse times the sheaf dual. And so a simple application of the theorem will tell you that the topological criterion which you need theorem, so at a simple wall, if sort of for all E which appear in the complicated locus, but actually usually you can't control which sheaves appear there, so you try to satisfy this for all sheaves E that you're thinking about. If the dimension of x, y, E1, E2, if this is congruent to 0 mod n, then you have some kind of invariance. You have the elliptic dt invariant on one side of the wall, so for the stability condition sigma minus, specialized to some nth root of unity, is going to be equal to the elliptic dt invariant on the other side of the wall, again specialized to some nth root of unity. And okay, maybe I'm. What is x sub y? X sub y is the alternating sum of the x groups on y. Y is the threefold. Oh, I'm so yes, okay. This is a capital Y. Yeah, it's maybe more obvious in text. Okay, so maybe I'll say the rest verbally. So, of course, usually walls are not going to be simple. And when you have a non-simple wall, there is some extra machinery you can do that sort of resolves your simple wall into that resolves your non-simple wall into a whole bunch of simple walls. And you cross those simple walls one by one. And the cost of this is that you're replacing your moduli stack or space of sheaves with moduli stack or space of sheaves with some extra data. And you have to play some combinatorial game with the extra data to make sure that you satisfy this topological criteria. And in some cases you can do this, in some cases it's not so clear how to do this. One case when it's very easy to do this is when your underlying Calabi-Yau threefold is actually the total space of the canonical of some smooth projective surface. So this is called when you're a local surface. And in this case, Donaldson-Thomas theory is also known under the name Vafa-Witten theory because this situation was originally studied by Vafa and Witten quite a long time ago. And in that case, it's very easy to control the dimensions of these X groups. You can write them in terms of some X groups on the surface itself. And then you get some slightly stronger statements. In general, for some Donaldson-Thomas theory on some arbitrary Calabi-Yau threefold, maybe it's not so easy to understand when the dimensions of these alternating sums of X groups will satisfy some congruences like this. Okay, so I'll stop there. Thank you for your attention.
Are there any questions?
Just a naive question. So what does elliptic over 2 and virtual over 2 mean?
Yeah, so somehow this is just notation. It's sort of supposed to remind you that one, this is some elliptic quantity, and two, that if you compare the definition of these elliptic over 2 things with the original definition of elliptic genus, you'll see that somehow we took what was originally in the denominator and we didn't take what was originally in the numerator. So somehow there's like half the stuff.
Thanks.
sitting aside of its cotangent bundle.
Yes.
That's kind
Yes,
of,
exactly, exactly.
so,
Right.
so in that sense, it's not, you shouldn't really put over 2 there.
Okay. Well, you know, the notation is something that I made up, so you're free to somehow use whatever notation that you like. Yeah. But somehow the name virtual chiral elliptic genus, that's not due to me. And somehow there's a previous notion of virtual elliptic genus, which is not the same thing as virtual chiral elliptic genus. And somehow the precise difference between the chiral version and the non-chiral version is that the chiral version is somehow half of the non-chiral version. Somehow the non-chiral version, the actual virtual elliptic genus, that's something that's existed for quite a long time, but somehow it's not very amenable to any sort of wall crossing technique for various technical reasons. Yeah. So somehow, if you want to execute this wall crossing story, it's important to have this kind of halving procedure, this kind of chiral virtual elliptic genus.
Okay, so from my limited understanding, you are trying to deform some kind of geometric structure. So can you transform this deformation into some differential equations, and then the wall crossing formula we can understand through differential equation?
That's a good question. I don't know of any sort of productive way to reformulate it as some kind of differential equation. For me, this is some relation that really arises out of equivariant localization.
Is there some examples of concrete calculations of elliptic genus?
Yes, of course. Right. So for the original sort of classical version of elliptic genus, which I wrote down, you can really try to just write down what it is for some toric manifolds, where there you have some really some torus acting with isolated fixed points, and it really has a very explicit form as some sum of some products of rational functions of theta functions, something like that. It's as explicit as you could want. More generally, even these sorts of elliptic Donaldson-Thomas invariants, which I'm writing down, or more generally these virtual chiral elliptic genus, which I've written down, these can also sort of be calculated by equivariant localization in nice situations. I think that's as explicit as you could want. Yeah, sort of. It's clear by design. We sort of design things. Yeah. I mean, so this has to do with the discussion at the beginning of my talk, where you really have to verify that this quantity you wrote down satisfies some Q difference equation. Right. So there's some non-trivial constraints on maybe will some nth root of the canonical exist, something like that.
Okay, we are 10 minutes over time, so maybe it's a good point to stop. Henry again.